Now that you've done the basics of motion and kinematics and stuff like that, we're going to start moving into what actually creates that motion in the first place. And we start talking about what actually causes things to actually move and cause things to accelerate. Well, that is forces. And when you start looking at forces, that is the topic of dynamics. And dynamics is all about forces. Okay, so that's like our next main section. Now, of course, forces or dynamics in general, basically, you've got the dynamics, which is the forces, they basically cause motion, which of course is the kinematics you guys have done. So dynamics or forces cause the motion, and then that motion is what we call kinematics. You guys have taken the kinematics part, you guys have looked at the motion, so now we're going to look at the actual cause of the motion in the first place, and that's where we're going to talk about forces. And there's lots and lots of different kinds of forces out there, and we'll look at a whole bunch of the different ones and look especially the common ones and how we can actually connect them to what you guys have done. Now, more specifically, when we talk about forces causing motion, if we get more specific, when they cause the motion, they actually cause things to accelerate. And when they do cause things to accelerate or give them acceleration, that's what leads into the kinematics. So there's sort of there's forces, which is the main part of dynamics, and you've got speed, which is the main part of motion, and it's sort of like acceleration sort of ties those two things together. It's sort of like you've got forces, and capital F is for forces, and you've got speed and velocity, which of course is the main thing for motion. You have to have a speed or velocity. Well, you've got this acceleration in there. So you got the acceleration in there, which actually sort of like ties the two things together. So, forces cause things to accelerate. That acceleration then causes things to have velocity. So acceleration sort of binds the dynamics and the kinematics together. All right, so that's sort of the basic idea behind it. Okay, well, let's start looking at some basic force type stuff. Now, when you start talking about forces, there's lots and lots and lots of different types of forces out there, but there are sort of some main forces out there. Sometimes they're called fundamental forces and stuff like that, but there's sort of main forces out there that basically are the main categories for all other forces, like sort of like the top categories. And realistically, there's actually 4 main categories or main forces. There's 4 of them. And all other forces generally fall under the categories of these 4. Now, we start looking at the ones that are the most common forces, the ones that you think about or whatever in everyday life and blah, blah, blah. We'll start with the more common ones, then we'll get to the ones that you probably never even heard of or thought of before. And probably one of the top ones that people think of or refer to when thinking about forces is good old gravity. And gravity is one of the 4 fundamental forces. And of course, gravity, this has to do, it's connected to mass. And a lot of people think about space and stuff like that, and gravitational fields, even black holes and stuff like that. And that's one of the 4 fundamental forces is gravity. And of course, gravity has a lot to do with our everyday life and stuff like that. So it's really, really common. Now, the other one that is super, super common for what we do and all that kind of stuff is actually electromagnetic. Now, you might not have thought of that one, but electromagnetic forces actually govern a huge amount of stuff that we do. And of course, electromagnetic forces, these are like from charges, like subatomic charges, like electrons, protons, stuff like that. So they come from electric charges, and they actually have a lot to do with our everyday life. For example, when you push something, when you apply a force on something, and you push a box, what are you actually doing? Well, what you're actually doing is there's actually like electrostatic repulsion between the electrons in your hand and the electrons in the box. And it's that electrostatic repulsion that actually causes the box to actually be pushed away from you. So what you're actually doing is you're actually electrostatically repelling the box away from you when you actually push it. And this is true for all types of pushing, where you're pushing a door or pushing a box or pushing a person. It doesn't make any difference. It's all the same type of thing. So electromagnetic forces actually have a huge amount to do with the majority of all the types of motion that we work with in our everyday lives, whether it's walking and or pushing something or cars driving, like a lot of it has to do with electromagnetism. So that comes from electrostatic charges and stuff like that. Now, these are the two main forces that you deal with in everyday life and that type of stuff, blah, blah, blah. Now, there's two other ones that are a little bit more, you probably never heard of them before, you may never hear of them again type thing, but they do exist. There's one out there that's called the weak nuclear force, and there's also what's called the strong nuclear force. And both of these forces are only relevant like at the subatomic level, and that's why they don't really have anything to do with you guys that you like actually would know. Gravity and electromagnetic occur at huge levels, no problem, can easily observe it. The nuclear forces, not so much. Now, the weak nuclear force and strong nuclear force, they sort of have different properties and attributes. Now, the weak nuclear force, this one is actually more about, this one sort of like, sort of holds things like subatomics together. Sort of holds subatomics together and binds them and stuff like that. It actually has to do with like radioactive decay and radiation, that type of stuff. The strong nuclear force, this is actually, it does a few things, but one of the main things it does is actually binds the actual nucleus together. So you've got like the protons, neutrons, and stuff like that inside the nucleus, and it's the strong nuclear force that actually binds that nucleus together and holds that core of the atom together. So the weak nuclear force is about like individual particles that make up atoms, where the strong nuclear force will actually bind, especially like in the nucleus, because you get all those protons and they don't want to be around each other, but it's that strong nuclear force within that nucleus binding the protons and neutrons together to lock it in. And it's that strong nuclear force that when that strong nuclear force is broken is when nuclei will split and you get like nuclear reactions and stuff like that, which are so incredibly powerful. So weak nuclear force is more about like radioactive decay and materials breaking down and stuff like that. Where the strong nuclear force, this is where you get your big nuclear reactions. So again, those last two though, like these two right here, you're not going to really encounter those in everyday life that you'd actually notice. It's the first two that really dictate the majority of what we do and how things work and stuff like that. Now, another sort of little thing, of course, that kicks in when you start looking at forces is how they actually work and the general rules. And when you start talking about like the rules for forces and how forces work, that is where a really important guy kicks in. That's when this guy kicks in, and you may not recognize him. That is Isaac Newton, and of course Newton's laws for dynamics and forces. They sort of like are the guidelines, the rules, the whatever you want to call it, of how forces generally work. And he sort of laid all the foundation for the stuff and published it and stuff like that. So it's typically in earlier science classes, I think even in elementary school and stuff like that, you often talk about Newton and Newton's work and stuff like that and forces. And he sort of laid out Newton's laws, or what are known as Newton's laws for forces and dynamics. So if you're going to start taking forces, it's really important to, of course, lay out Newton's laws of forces and how they actually, forces generally work overall like that. I like to think of it as the guidelines or the restrictions or whatever you want to call it for how forces do the things they do. Now, there's different ways that you'll see them written and stuff like that. I like to paraphrase mine a little bit more to make a little more sense to myself. But Newton's first law for motion and forces, that type of stuff, you often hear stuff, an object will stay at rest or will move in a constant way unless acted on by unbalanced, blah, 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 blah. Generally, Newton's laws or Newton's first law can be sort of condensed into one word, and that one word is inertia, which you may have heard of before. And basically the idea for inertia, and this is the way I like to think of it, is basically an object or whatever it is, an object will actually sort of resist acceleration. I'll put resist in quotation marks because obviously they can't resist, but objects will resist acceleration. They don't want to accelerate because that requires force. So if an object is just sitting there, it just wants to sit there. It doesn't want to accelerate. And if something is moving, it wants to keep moving the same way it's moving. And if it doesn't, that would require an acceleration. So I like to think of it as objects will try and actually resist acceleration, or another way I like to think of it is they sort of want a constant velocity, and that velocity may be equal to 0, but basically they don't want to change their velocity. And when you try and change their velocity, they will sort of resist, so to speak. They don't actually resist, but a force will be applied back. So that's my basic idea for Newton's first law, which is inertia. Objects don't really want to accelerate, okay? And that's where if they do want to accelerate them, you have to supply a force, okay? And that's basically Newton's first law. Newton's second law is sort of like the calculation law, and most people think of it as a force law, but it's actually more about the acceleration. It's sort of like it's more actually about the factors of acceleration and what dictates how much acceleration you can actually get. And there's two main things that dictate how much acceleration you will actually get. One of them is the force that's being used. So the more force you use, the more acceleration you're going to get. And of course, the other thing is the mass of the object. Where the more mass there is, the less acceleration you get. So force and acceleration are directly connected to each other. As one gets bigger, the other one gets bigger. But mass and acceleration are inversely related. The more mass you have, the less acceleration you get. So if we put that together, you get acceleration is equal to force divided by mass. So as the force gets bigger, acceleration gets bigger. But as mass gets bigger, the acceleration is going to get smaller. And most people just rearrange it and just remember this as F equals ma. And that's the way most people remember the second law. Now, you have to be a little bit careful with this, though, because the force is actually pretty specific. It's not just any force. This right here has to be the net force, which is the total force acting on the object. It's not just whatever forces are there, whichever one you want to use. It has to be the net force or total force in the situation. That's what net means, is total. There are always forces acting on you, but you're not always accelerating because the net force might be 0. Things are canceling out. So you got to be really careful, and that's why you'll often see net force equal to ma. Now, sometimes there's only one main force in the situation that's relevant, and it's no big deal. You use that one force. But when you've got a combination of forces, you got to put them together and work with the net force to get that acceleration. Okay. Now, the third law, most people know this one as something along the lines of some either like action, reaction, or for every force there's an equal and opposite force, blah, blah. I like to paraphrase it a little bit differently. Basically, the way I like to put it is all forces, no matter what, all forces come in pairs. There's always two. And these paired forces are going to be equal and they are going to be opposite. And that's the way I like to look at Newton's third law. So you've probably heard these before. I just like to paraphrase them a little bit differently. Makes sense to myself. And there's other logistics along that go with them that we can discuss some other time. But those are the three main, or not three main, those are the three Newton's laws. And they sort of guide how all forces, not just gravity, not just pushing forces, all forces, no matter what they are, they follow these general guidelines. And this is a huge important document and publication for mechanics in general. And it was typically introduced sometimes in elementary school with Newton and some stuff, but also in grade 10 science in your mechanics units. You guys look at this a little bit, I believe, but we will expand on this quite a bit. Okay, so you got the inertia, basically objects resisting acceleration. F equals ma, that's the main one that will be, really cranking, because that's where the calculations kick in and we can actually find stuff. But keep in mind that there's always forces, they're always coming in pairs, they're always equal and opposite, which is the third law. Okay, so next what we'll start doing is we'll start practicing using these forces, laying out different types of forces and how they connect to each other, and then connect it to your kinematics you've done. Okay, so let's just do something really simple to sort of show you how this works. So, let's take a surface or something like that, no big deal. Okay, and here, whoops, color, there we go. Now, here, we'll even make a fancy schmancy box. There we go. We'll even fill the inside. We can even put a couple wheels. There we go, good enough. And let's have, here we go, person pushing the box. Okay, super classic, everyday, blah, blah, blah type example. Really simple. Okay, so it's pretty straightforward. Suppose we got a 75 kilogram box, and let's say this person is pushing with, let's say pushes with 300 newtons. Of course, force is measured in newtons, of course, named after Newton, duh. Okay, but he's going to push with 300 newtons, and just really simple. So what's the acceleration of the box? Okay, well, really straightforward. F equals ma is the general expression. So if we want acceleration is force divided by mass, and this is the net force. So let's go look at the forces involved. Let's see, how much force is trying to move it? Well, he's trying to move it with 300, and I would often call this the applied force, because that's the force he's actually applying. So I got my FA of applied force of 300 newtons. Well, there's no friction, there's nobody else pushing or pulling, nothing. That is the only force involved. So that would also be my net force. There's nothing else really going on. So I've got 300 newtons of force. The mass of the box is 75 kilograms, and 300 divided by 75 would just be 4. So the acceleration of the box would be 4 meters per second squared, and that's it. Okay, so that's the basic idea behind Newton's second law. Now, what if we just modified this a little? Let's change this up a little bit. Let's take the exact same situation, exact same everything. But now, maybe, just maybe, there is 25 newtons of friction slowing it down. Okay, so what would be the acceleration now? Okay, well, it's going to be pretty much the exact same thing, except we got to take into account friction. So, of course, he's pushing with 300 newtons this way, and friction would be kicking back with 25, trying to slow him down. So all you have to do is you got 300 and you get the 25, you just got to subtract the two, and that would be your net force. So in this case, the net force would no longer be the 300, it would be 275 newtons going towards the right. Okay, so again, acceleration always want net force. When there was just the one force, no big deal. But if there's multiple forces, you sort of piece them together to get the net force. So now we can do the same type of thing. Acceleration would be the net force divided by mass. And in this case, now the net force is the 275, not the 300 we had before. So of course, the acceleration is going to go down, and we get around 3.7 meters per second squared. So this is just the difference between, just basic F equals ma, but also the importance of net force. And that's why when I write F equals ma, I don't put applied force, I don't put just whatever force. I usually try and put down net force, whether there's only one force or if there's multiple forces. It's always about the total force acting on the thing. Okay, so there we go. So that is a very fundamental dynamics type question. Okay, so let's do another one and see if we can then incorporate some of the kinematics you guys have done as well. Okay, so here we have SpongeBob in his car, or I guess boat car, boatmobile, whatever you'd want to call it, doesn't matter. Anyway, so let's say it is, give or take, let's say it's 820 kilograms, and let's just start super simple. Let's just say he's sitting here at rest, so he's not going anywhere. And let's suppose you had a little motor in the back there. Let's say the applied force from the motor is 2,000 newtons. Okay, so what we're going to do is we're going to find out, we can find out a couple things. Let's see, how far has he gone after, let's just go with 5 seconds. Okay, so how far has he gone after 5 seconds? Okay, so let's just start simple. Let's just start basic. Look what we got, piece a few things together and see what we can do. Now, you've got force, you've got mass. There's no other forces. We're not going to worry about any other forces. You've got force, you've got mass. It's the only force involved, the 2,000, so we can find the acceleration. So let's do that. So the acceleration of the boat would be the force divided by the mass. It's the applied force is also the net force. It's the only force we've got. So we'll just divide those two out, and we will get the acceleration of the boat, which would be around 2.44 meters per second squared. So there's the acceleration of the boat. Okay, well, I've got the acceleration, but I've also got the time. And of course, with acceleration and time, I can find the change in v. So again, kicking back to what you guys did with kinematics. So with that, the change in v would be acceleration times time. So of course, that's going to be the 2.44 we just found. Multiply that by 5. And our change in v is going to be like 12.2 meters per second. All right, so if we map things out, well, SpongeBob here starts at 0 meters per second and sped up to 12.2 meters per second. And right in the middle would be his average V of 6.1 meters per second, which of course is what we would need to calculate the distance, because of course distance is just dtv. We have the time of 5 seconds, no big deal, and the average V would be the 6.1 that we found after finding the average V. So we're just going to take that 5 seconds, multiply it by the 6.1, and then we can find out how far he went, which of course, round off, is going to be around 31 meters. That's like 30 and a half. So like 31 meters is how far he's gone. Okay, so that's basically how the dynamics really connects to the kinematics. So there really isn't a lot new. It's more about, use the forces to get the acceleration, and then use the acceleration the way you guys are doing in the previous unit. Or you use kinematics type stuff to get the acceleration, and then work backwards to actually find the force that was used. And that's basically it. So not a whole lot new. Really, there's only one new expression, but there are different scenarios and possibilities and specific forces that we'll look at in situations, but it's all very similar in terms of the applications.